Okay, welcome back to the 424 School of Engineering. Thank you for joining again. And today we will talk about Laptime optimization, something obviously very important given the mission of 424 to break the lap record at the Nürburgring. So really excited to show you some of the analysis that I have done in the past and recently um, in order to make some critical decisions when deciding about aerodynamics, managing the power around the lap, the weight of the car, things like that, first order parameters in order to really get into that high performance window. So we're going to talk about this in a minute. First, I'm going to show you something I am working on very quickly that I'm quite excited about. And obviously looking at the bigger picture of the team and how we're going to develop as a network and as a team. Obviously, so this is something I'm working on. It's work in progress. Okay, just to illustrate the way that we're going to create a token for the team that we're going to call the PRN token. And eventually this token is something that will go on a crypto network and that anybody around the world will be able to buy and sell. And the idea is that this token will represent the ownership of the team. And this is what I believe is the best way to create the network, the open network, the team that we are developing. This is not new. Obviously, we've been using the concept of a token for years now, and I have explained to you already that we have more than 80 people who own the pairing token that have contributed into the 424 project and the pairing team as a whole over the years. But obviously, I want to develop that side of the team more, and I am also connecting with people in the business side to really try and make this stronger and develop the team for the future. We have really big plans here. It's not just about 424. 424 is one part of a bigger picture, and pairing is really about creating a new platform, a new team that will develop 424, but also other projects in the future. Okay, so I've just started this, but you will see images soon on social media about this token, just to give a picture for everyone, our followers, our community, about how we go about the business side of pairing, and we call it tokenization of the team. So creating this token which allows to give access to everyone when it comes to ownership of the team, and obviously making, distributing the returns from our projects to a wide community and not just a small number of shareholders. Okay, so keep that in mind. I wanted to show you that today. But if we come back to what you're here for, lap time optimization. So just I think there is a question from Lauren about what I've just explained. Lauren, did you raise your hand?
Can you hear me okay, Rico?
Yes, I can.
Yes, perfect, excellent, thank you. Thank you for explaining things about the token as well. My question is, how can we actually invest? I know that at the moment you're fundraising for the simulation. So how can we actually go about investing? Is it all online or do we contact you personally?
Yeah, thank you that's a great question. So at the moment, you can invest directly on pairing.com, and effectively there is a contribute page. You can go there, and if you have an account on pairing.com, you can already contribute some money towards the fundraising, which is for the simulator. But what's going to happen is this is very much linked to the token that I've just talked about. So we already have a database where we register every contribution and every investment, and in the back end, you receive tokens already. So when you go on pairing.com, which I can show you quickly, effectively, when you go in the directory here, that you can see is the list of all the people who own tokens already, okay? And these people have simply gone on contribute here and basically bought, at the moment it says credit, but it's effectively the same thing. What I'm gonna do is I'm gonna rebrand everything under the token and make it more clear that what you're buying is this token that will eventually have a price fluctuating and increasing over time. In the bigger plan is that this token will become a truly a crypto token that will be on blockchain. This is not the case just yet, but effectively the token that you can buy today on pairing.com will be put on the blockchain soon, and all the tokens that I own and everybody else owns, they will be basically put on the blockchain soon, and the same token will then live in the blockchain. Okay, so we are just going through a step-by-step transition towards a blockchain and crypto technology. So you can already buy this token. Okay.
Okay, thank you so much, Nico. That all makes perfect sense.
Great. I'm glad to hear that. Okay. Thank you for your question. If anybody else has got any question about this, don't hesitate. We'll keep talking about this. Obviously, it's an important part of how the team is going to grow and how everyone will be able to get involved and invested and be part of the pairing team. Okay. So Laptime optimization. Today, the session might be a bit shorter than usual. There is less to cover, but I want to dive in the details of certain analysis that I have done. So obviously, I love this challenge that we have to try and sell this lap record, because one thing that I love about it is this lap, the Nürburgring track, is like nothing else that I have worked on before. It's much longer. Typically, Formula One tracks are 4 to 5 kilometers long. This one is 20.8 kilometers long. It's a lot of elevation change, a lot of camber change. It's quite bumpy in places, even though they're making it smoother and smoother by resurfacing the track. But also, there's no runoff area. We have to make sure we don't go off the track. There is very little margin when it comes to safety. So I really love this challenge. It's the 5-minute lap, especially with the electric car. I will explain today the challenges that we have and how we can optimize around those challenges. I like to start today with a summary of the bigger picture of I call it I guess the race to setting lap records at the Nürburgring. I'm highlighting here obviously the fastest cars on this track. I've added one actually. You've heard maybe of the Lotus Evija or Evija X, which is a special version of a production car from Lotus. It's a full electric car, and they've just announced that they've set a lap of 6 minutes 24. It was actually done in October last year. The reason I've put this lap here is to put it in context of what we are doing with 424. Obviously, the electric record is the Volkswagen IDR in 6 minutes 05, and that was done in 2019. The IDR is closer to it. It's a pure race car. It's a prototype, where the Lotus is effectively a production car that they've adapted for the Nürburgring. But if you look at the lap times, 6 minutes 05 for the Volkswagen, 6:24. I worked, as you know, on the Neo EP9 in 2017. Before the Volkswagen, we actually set an electric record at the time in 6 minutes 45. This car used to weigh, the weight of the car was about 1.7 ton. The IDR, I believe, is 1.1 ton. The Lotus was 1.7 ton before they made that special version, and I would imagine they've probably, removed 200 kilos of the car. But I know from the media that the battery itself is 700 kilos. Remember, the 424 is 1 ton, 1.0, and the battery itself is 300 kilograms. So you can see that the Neo EP9 also had battery of about 650 kilos. So you can see the importance of mass, and also the fact that 424 plays in a completely different category. It really plays with the Porsche 919, which obviously is hybrid and is the 5 minutes 19 that we all know about. And in simulation, yeah, we are low 5 minutes. We've actually achieved once 4 minutes 59, so I've put it there. But you will see in a minute that we are basically playing in the low 5 minutes, depending on the battery specification that we're going to use. But we are, we are much faster than the current electric cars. And there is a good reason for that, because the car is specifically designed for the Nürburgring. The Lotus is a production car, and then it's adapted to the Nürburgring. So it's not purely optimized from a design point of view for that lap. It has been adapted, but not fully designed for the lap records. It's got a passenger seat. It's a production car. It's a totally different concept to start with. The Volkswagen actually was designed. The chassis itself comes from. It's a tubular steel chassis, so it's not as light as a carbon chassis, and it comes from an existing car that used to set records at Pikes Peak in America, and they did the Pikes Peak record first and then adapted to the Nürburgring. And again, they didn't design that car specifically for the Nürburgring from the ground up. The Neo, same, it's a production car. It was like, a Ferrari style car with a lot of carbon. So it was a mix between racing and production. 424 is one goal, 100% for the Nürburgring. This is the only way you can achieve the lap time that we're going to achieve here. And I want to reiterate how focused we are, because I see sometimes on social media other projects and people saying we've got this electric hypercar and we're going to set a record at the Nürburgring, maybe break the record at the Nürburgring. But these cars are never specifically made for that. They might be production cars or supercars that are sold to wealthy individuals, but they are not really specifically built for that. That's why I don't see any other projects at the moment that are as focused as us on the Nürburgring. And that's okay. This is where we put our energy, and that's why I believe we will achieve and be successful. So you've seen these videos before. I've put them here again, but we're not going to play them just now. But I like to remind everyone that we have the onboard lap on YouTube. Obviously, that comes from our Unity simulation. We keep driving the car every week in simulation, but this onboard is quite interesting to look at compared to the 919, and you can see what's going on between reality and simulation, and I think it's a good way to look at the track model and how accurate the track model is as well. So there's going to be 2 sections today. Effectively, we're going to spend the most time talking about the offline lap time simulation. I'm just going to reload this because it looks like things haven't loaded properly. Here you go. That's better. So in the first module, we talked about the offline lap time simulation, and we're gonna dive into the details of some of the analysis done in this tool and how important this tool is for the work that we've been doing up to this point. So we're gonna open this in a minute. And the second section is the dynamic lap time simulation in Unity. And we've talked about it a lot. And I will just explain a bit more what we do with this compared to the offline tool. When it comes to lap time optimization, depending on what you're trying to optimize, you either use the dynamic lap time simulation, that you need a driver for that, and it's obviously a much better model, or I use the offline lap time simulation, or I use both. Well, typically I would, for things like weight, um, so first order parameters, aerodynamics, power, strategy around the lap, that will typically I will start with the offline lab simulation. Yeah, there's so much you can do there very quickly. And when I have something that I want to then validate or test, I then go in Unity and ask the drivers to test the specific setup that I have found in the offline simulation. Okay. So with the offline lap time simulation tool, which is it's basically a Google spreadsheet or a Google Sheet document with a script running in the background, and it's something I've developed for 20 years now. I started this tool at Reynard in 2001 as part of my end of study project, and it's a tool that I've been developing over the years and um, allows me to do specific analysis, and I will show you some examples because I can change the script as I need. But the aim really is to be able to produce some speed profiles that you can see here, effectively going around the trajectory of the Nürburgring. There are some limitations. The lap I'm going around is just a trajectory that comes from Unity, but it doesn't have elevation, it doesn't have camber, so it's a completely flat track. And also you can see there are features we cannot replicate. For example, the blue speed you see here is the one from Unity, and you can see some sections on the track where we apply some speed limitation. I explained that before. As a reminder, the reason why here and here and there, so there's 3 sections, we limit the speed of 4 to 4 because the car is going over crests and big bumps. And we found that we have to reduce the speed, otherwise the car will lose contact with the ground and can start taking off and flying, which is a bit scary. But in the offline simulation, we don't have these features. But that's okay, because what we want here is sensitivity analysis. Even if the lap time coming off the offline simulation might be 10 seconds off, compared to the Unity simulation that we believe is more accurate, it's still good enough to start playing with parameters and looking at sensitivities. Sensitivities is the idea of I change mass or downforce by 1% or 10%, and I want to see the impact on the lap time. Not only lap time, but I also want to see how much energy I consume and how much thermal load I put on the battery. So that's an important thing that we're going to look at today. If you look on this plot here on the right, that's one of the analyses that I have done. So typically the blue trace is lap time for different setups, and this specific one is different level of drag and downforce. And I'll show you in a minute the numbers. So there is an optimum point for lap time, and you can see that the lap time is 4 minutes 52 in this case. And if you reduce the drag, downforce, you will start losing up to 4 seconds, and the other way you will lose 4 seconds as well. You see the importance of trying to be in the right window here. 4 or 5 seconds might make or break the record. We are really playing small margins against the 919. It's so exciting, I think. So every 2 seconds really matter for us. The red trace is the battery power RMS. So RMS stands for root mean squares, and it's a way of, it's basically an average, but a slightly different way of calculating the power average around the lab. It's a more accurate way to look at the average when it comes to battery temperature. So if you want to cool your battery down, you want to lower the power RMS around the lab. The reason I'm talking about this is one of the limitations for the record in the electric, with the electric powertrain, is the temperature of the battery. So when I started this project, I thought straight away, the limitation might be energy. We might not be able to have enough energy. It turns out that actually around the full lap, we consume about 43 kilowatt hours, and it's not a crazy amount of energy, and we have solutions for that. But actually, one of the limitations we find when I work with the battery suppliers is the temperature is going to be critical, because the discharge and regen is so aggressive around the lab that we are going to be really on the edge, on the limit to finish the lab and stay below the maximum temperature allowed by the battery cells. And I think if you know a bit about battery and electric mobility, you know that effectively one of the limitations of batteries is if the temperature is getting too high, they might start what we call thermal runaway, and that could turn into a catastrophic fire. So definitely not something we want. What will happen is if we reach too high temperatures, the battery is going to start derating. It will automatically reduce the power. Even if the driver is going full throttle, automatically the battery is going to derate and not deliver the full power that we're asking for. So imagine we're at the Nürburgring, we've got everything set up, and we go around the lab, and you start the back straight here, that long straight between turn 43 and 44. By the way, the turn numbers start 1, 3. This is the Perrin 424 map. We've created this map, and we've put instead of using the names and the German names for corners, which I still don't know myself, I'm used to talk turn 1, 2, 3, 4, like in Formula One and the racing categories. So this is the official map that we will use when we go at the Nürburgring. And you'll hear the driver, commenting about turn 11, this, or turn 30, 39. I mean, there's 44, 46 corners in our case. There's more because they say the track has got 78 turns. But what we've done here is we've isolated the main corners when we actually brake or slow down. Some corners are flat and we don't consider they are corners. Okay, so we are going round, and typically the driver will be in the back straight and he will see the temperature creeping up and will be really, really close to the limit. And because depending on how is driven the lap, it might be that the temperature has gone a bit higher than our simulations or the lap before, the previous lap it did, or the ambient temperature has increased and the temperature is higher. And it could be that our lap time is very good and we're about to break the record. Just imagine that. We're about to break the record, and actually 200 meters before the breaking point, battery starts to derate because the temperature is too high, and you're losing very quickly. You're going to lose 4 or 5 seconds. And we cross the line and we don't get the record by 2 seconds or 3 seconds. That could happen. So it's a really interesting exercise to try and manage the battery temperature around the lap, not wait for the last section of straight to cool the battery. Because if you wait for the last section of straight, as I said, you might lose a lot of time doing that. So what you want is to manage the temperature before, and I'll show you how we're going to do this. Okay, so it's optimizing lap time for various limitations and coming from, as I said, mainly the battery in our case. Okay, let me open this tool now. So you've seen this tool before. there's a number of tabs at the bottom: Nordschleife, Monza, Silverstone, Spa, Bahrain, Le Mans. So that's a small list of tracks that we've got data for. The one we're focusing on, the Nordschleife. And for each track, we have 5 channels. We've got time, distance in meters, speed, lateral acceleration, longitudinal acceleration. This is coming from outside of this tool. This might come from a real car with sensors, or in this case, it comes from Unity simulation. That allows us to basically draw a trajectory, which you can see here. So it's a 2D trajectory at 10 Hertz. There's 1 point every 10th of a second. You recognize the Nürburgring here. And this is what the script is taking and driving the car around. So if I come to our main page, I went through that before, but just as a reminder, the parameters we have here is the overall transmission efficiency for the car, the rolling resistance for the car. The car is just a point mass. Okay, it doesn't have 4 tires and suspension. It's a very simple model. The total weight of the car, 1,000 kilos, SCX, SCZ, drag and downforce. The grip at 2 different vertical loads. And then the vertical force distribution, because a 2-wheel drive car and 4-wheel drive car will not have the same capacity for acceleration. The grip of the track. And then we've got these power maps. So for each test each column is a test, is one setup we're gonna assess. And this is the power map. So depending on the car speeds, we have different power. In this case, it's 800 kilowatts all the way. But actually, when you reach 360, the power is going to go down to 0 in a window of 5 kilometers an hour. This is how the speed limiter works on 424. We don't have it's a very simple way of doing a speed limiter. The power is calculated as a function of the speed of the motors or the speed of the car. And it works really well, and it creates this speed limiter here. And you've got other parameters, which some of them are new compared to the previous modules that I did. So the speed limiter is effectively another way to do speed limiter. So you can either do power decrease with speed. What I did in this software is I added another way to do speed limiter. It's just a cap on the speeds, which we cannot do in Unity, but it's an easy way to, instead of going through the power map, it's an easy way to reduce the speeds, the top speed of the car very quickly. The power bleed is a feature that I tried but didn't really work, is the idea that the power of the car would reduce over time in a straight line. So how many kilowatts we would lose per second, but it's not something that actually came as an optimum way of managing power. We've got regen power on the car, okay, with an efficiency. So when you regen, not all of the energy that you have harvested can be reused for the propulsion of the car. It's just because of the way the battery works. This is the same as for drive, but it's for braking. So how many tires do you use to regen? Because again, you cannot. It's not like all wheels are regening at maximum power all the time. Now this one is interesting. That's a new one. The lift and coast parameter. So what is lift and coast? This is something that cars do in the WEC at Le Mans, but also a lot in Formula E. It's basically releasing the throttle in a straight line, but not braking. So you lift the throttle or the power goes to 0. You let the car slow down as you approach the corner, and when you arrive in the braking area, then you brake. So there is a coasting time. There is a time where the car is not accelerating, not braking. It's slowing down just because of aerodynamic drag. And the parameter I use here is at what speed the brakes will come back on which means, and you can see they're all 400 means that feature is out of the way, it's not used, 400 kilometers an hour. But here you can see 265, and that means the software will calculate the lift points. So in a straight line, the power will go to 0, the car will slow down, and it's calculated so that the braking point happens to be at 265 kilometers an hour. So imagine every braking zone will happen in this way. The driver will lift off the throttle. In fact, in 424, it will be automatic. We're going to map the track, and we will ask the car to reduce the power automatically when it arrives at a certain point. And it's calculated in a way such that the car slows down and reaches about 265 kilometers an hour when the driver needs to brake. The driver is not going to look at the speed and wait for that speed to brake. He will brake when he needs to, but it will be adjusted in such a way that we always arrive at about the speed of 265 kilometers an hour. The reason, if you do that every single braking point, this is actually, from my experience with Formula E and everything that we do at Le Mans, this is the best way to cool your powertrain or your battery down without losing too much time. Okay, I'll show you in a minute why this is faster than doing something different. Okay, I want to show you, first of all, the aerodynamic optimization that I did, and then we are going to look at the power optimization for the battery. So for that, I'm going in this tab, Notch Life Optimization, and I'm not going to go through all this text, but there's a couple of things I want to show you. First of all, as I said before, what we are optimizing here with this tool is the weight of the car. Effectively, the weight is an arbitrary number that I know we can build the car at, and I want to keep it at 1,000 kilograms. We could make the car heavier. What it would give us is potentially a bigger battery and more power. Or we could make it lighter, but we'd have less energy and less battery. So as the first optimization I did was looking at energy versus car mass, and I found 1,000 kilograms to be a really good place to be for us. So I will not detail that today, but I just wanted to tell you this. Now, SCX, SCZ. So first of all, remember the car has got DRS, drag reduction system. In Unity and in real life, the way we're going to do it is automatically when the driver is full throttle for half a second, more than half a second, DRS is going to open automatically. Okay. As soon as the driver lifts the throttle or applies the brake, the DRS will come back and downforce will come back. Now, in this tool, offline simulation, we don't have DRS. So what a very good approximation is to use a drag number that is when DRS is open, and a downforce number that is the downforce when the DRS is closed. So this model is going around the track, assuming a low level of drag, which is DRS always open, and a high level of downforce, which is DRS always closed. Now, we know that this is not what's going to happen in reality, but in terms of vertical load in the corners, this is the most realistic scenario because we have DRS closed. In terms of drag in the straight line, this is the most realistic scenario because this is when DRS is open. So I found that using this simple model, we get actually very good sensitivities around the lap. And that has been validated in Unity against the tests we do here. The top speed is fixed at 360 kilometers an hour. This is not only based on pure optimization, it's also a constraint we have with the maximum speed of the electric motors and also the loads that we can apply on the tires. Okay, so this is like a self-applied constraint for the project. Here I detail some of the link between the mass of the car and the energy that you can have in the battery. So I'm not going to go into the details of this, but as you can see, there's been work already done on how much energy we want in the battery versus the mass of the car. And we know how much lap time we lose for 1 kilogram added to the car, which is about 1/10 of a second. And we also know how much lap time we gain for extra power to the car. So that analysis has been done in this tool as well. Now, one thing I want to show you is aerodynamics. So here we have a very important table. I'm going to show you this plot here. So in order to optimize aerodynamics, drag, and downforce, what we're trying to find is what we call the drag level. That's what Formula One does for every single track on the calendar. When they go to Monza, they run a low drag level, small wings. When they go to Monaco, they run a high drag level. And some tracks are in between. Spa-Francorchamps or Baku are tracks where they're medium drag level. For 424, it's the same. So let me show you a few points here. For example, the Le Mans car, the LMP one that I designed, is the green point. So this is drag, and this is downforce. And you can see the drag level was about 0.7 SCX. Remember, this is when the RS is open on this plot here. But just remember this: the Le Mans car was 0.7 SCX. When we go to the Nürburgring, if we keep this car at this drag level, we're actually losing quite a lot of lap time. I think it's about 10 seconds on the optimization curve. I will show you that in a second. So the important curve that I've created is this one. You've got what we call the 424 Nürburgring Polar. So effectively, it's the 424 car designed for the Nürburgring at different drag level. All I do is I change the size of the rear wing. I change the flap angle at the front to rebalance. I also do other things like the size of the gurney at the back. I might adjust the size of the front wheel arch as well, because these are the best ways to change the drag level. The floor remains the same. I'm mainly talking about these 2 points here. This point actually is an artificial point that I have added to get a curve. In fact, this one as well. Okay, so this point first is, imagine a car with no downforce. It would still have some drag. In fact, you hear Tesla or all the electric car makers now, they tend to announce their coefficient of drag. So we know that a car of a certain size will always have a drag level of about 0.25 if it has no downforce. As you're adding, downforce and wings, you're going up on this curve for 424. There are other curves as well here that came off previous analysis on the LMP1 car, just to show that most cars are working on a similar slope. What you're finding with 424 is we're extremely high level of performance. We're above all the other points. There is typically a point here for a Formula E car. You can see how low drag and downforce the Formula E car is. And this is typically a Formula One car. It's fairly high drag and high downforce, but actually we have more downforce on 424 for the same drag level, which is quite, it shows the level of performance. I'm not saying this is today's Formula One car. Maybe today's Formula One car are higher. They're probably in this region here. Now, what I needed to do the aerodynamic optimization is basically an equation for this curve. So I have fitted a curve through 4 points. These 2 points here at the top, these are coming from CFD analysis. So they're very accurate. In fact, the high point is the car that I have developed for the most time for the Nürburgring. And this point here, I call it the low drag level, I'll show you in a minute, it's the optimum point that we would use for a battery that has got less power. So the high point will be using the 800 kilowatts battery that we want. This point would be optimum for a battery of about 600 kilowatts. Just because we are looking at what battery we can find on the market. Again, these 2 points are coming from CFD. So all I did was changing the wings. I've basically shrunk the rear wing and changed different things on the car. So now I know that I can effectively choose where on the curve I want to be just by changing the wings. This curve has been fitted and I've got the equation here, okay? It's a quadratic model for the polar of the 424 car. Of course, it's a bit simplistic. There's no ride height change. It's a medium ride height point, but we have to start somewhere. We have to be able to do optimization in a way. Okay, so we've got this curve here, and now what I've done is, if you go into the aerodynamic 800 kilowatts optimization, this is like a snapshot of a previous analysis I did. All the cars, so I've got 6 cars. All of them are 800 kilowatts. All of them are 360 kph top speeds. All of them have got no lift and coast. Okay. And the only, in fact, the only change you can see here on this little widget, the only parameter I change is SCX, SCZ. So what I do is I sweep SCX between 0.75 up to 1.25. So I put a step of 0.1. So 0.75 to 1.25, if I come back here, it would be basically saying I want to test cars that are between these points going up to the top of the curve, 1.25 SCX. So I'm sweeping drag level on this part of the curve. And for every drag, I've got, using the equation of the curve, I've got downforce. And basically, you can see downforce going up and, basically increasing and decreasing. By the way, the maximum point here is this 8.65. I don't test over the maximum point of downforce because we know that we are increasing drag and reducing downforce. This obviously will be slow. So I test these 6 cars and I look at lap time. In this case, I didn't look at the battery temperature. It was purely a lap time optimization. And I found an optimum here, which is the 4 minutes 51. And the 4 minutes 51 is 1.05 SCX. So if I add drag and downforce after this point, I start losing lap time. But the other thing as well, you would actually look at what you know is your battery temperature is also going to increase as you add drag to the car and downforce to the car. The simple way to understand that is if you have more drag and downforce, the driver will be able to brake later, apply the throttle earlier. There is also the drag increase will mean you will not reach the speed limiter as quickly, and therefore you will use more power on average. Okay. So your battery temperature will be higher at the end of the lap. If your battery temperature is not an issue, then you go to the optimum lap time, which is what we did to develop 424 to its optimum point. And this is how we achieve in Unity the 4 minutes 59 lap. Remember that one. The picture you see here is the 800 kilowatts optimum drag and downforce to achieve the optimum lap time. That was effectively assuming that we can find a battery, or we can develop a battery that can deliver 800 kilowatts and be cooled enough. Now, the reality is, so remember this point here. Now, the reality is, at the moment, given the battery technology, we can find batteries that are lower power, more around the 600 kilowatts power level. So what I did here is I say, okay, let's re-optimize the aerodynamics for this case and see. I want to know what it will take in terms of modifying the car to re-optimize. Obviously, we're going to go slower because there's less power, but I still want to optimize the car for this different battery specification. So I did the same, exactly the same sweep of drag and downforce, but the power is 600. Everything else is the same. And the result is this. Now you can see that we've got an optimum lap time. Obviously, we've lost about 10, 12 seconds here compared to the 800 kilowatts, but the optimum lap time is at a lower drag level. So there's 2 points that are quite close, 8.5. So in terms of lap time, there's 2 points here that are exactly the same lap time. But interestingly, the power RMS obviously is lower with the lower drag level. So 511 kilowatts RMS versus 517 kilowatt RMS. So if I had to choose now what point I want to build the car or design the car around, if I had this battery, I'd say, let's do this one because I will achieve the same lap time as this one, but I will push the battery a bit less for the temperature. And if you look at this point, it's a drag level of 0.85. So if I come back here, this is 0.77, so it's just a bit more, so it would be about there. Okay, so I hope you're following. So basically, in steps, we optimized the mass of the car versus the energy. Now I've optimized the aerodynamics versus knowing the power that we have. But we're going to go one step further and focus on that 600 kilowatts battery and try and find a bit more lap time. And this is the last part I want to show you today. Okay, so now we are going to this tab here. And what I've done here is I've got 5 cars. Car number 1 is actually the 800 kilowatts, just as a reference. Car 2 is the 600 kilowatts at the optimum, sorry, at 1.05 SCX. So what I've done is between 1 and 2, I only change the power. And I am at 1.05, which is the optimum drag level for the 800 kilowatt car. Then car number 3 is we change the drag to the optimum drag level for the 600 kilowatts. You can see that the lap time effectively, we start at 4 minutes 51 for the 800 kilowatts car. We are losing 19 seconds in this case with the 600 kilowatts car. And then I regain 1.5 seconds by changing the aerodynamics. And now I want to reduce the temperature of the battery. Why? Because I know that my power RMS of 511 is still a bit too high. And given some analysis we've done on the thermals, we need to reduce the power RMS. So this is a new constraint that we have. We need to go from about 511 down to about 465 RMS. So I need to reduce the power RMS, but with the best, the optimum lap time. So what I started doing was I had 2 ways of doing that, which is car number 4 and car number 5. Car number 4, I kept the power at 600 kilowatts, and I applied lift and cost. So you see, before we had no lift and coast. Now we've got 265 kph. So I'm going to show you what it looks like on the speed. So we are looking at the orange here. You can see every straight line. So by the way, let's start in the order. So this is the 800 kilowatts car with the maximum speed in the straight and the speed limiter. Then we've got the 600 kilowatts car, and then the same with the lift and coast. So you can see every straight line, there is at some point the power drops to 0, and then the car slows down with drag. And when the driver knows he needs to brake, then he brakes. But as I said before, what we've set is the speed of the lift and coast, so the speed target for the braking point. It's not always 265, also because in the simulation there is it's a 10 hertz simulation, so there is an approximation on the points. But so here we are braking at 279 kph, here 276, 275, 269. But this is effectively a very good way to cool the battery without losing too much lap time. And as a last step, so when I did this, I lost 4.4 seconds, you see. But the battery RMS dropped quite a lot. Obviously, we will know only when we build the car at what sort of average power we can afford, to keep the battery temperature under control. And the last thing that I found by doing some fun analysis and experimentation is I can find another second. You see the 12.9 drops to 12.0, but the RMS is still 465. In fact, it's 465.5 here. So I've managed to go 1 second faster, which is, as I say, every second counts, 1 second is a big thing for us. I've managed to find 1 second, and by having the same battery temperature at the end of the lap. And the way I've done this is I applied what I call a power ramp. So I have scheduled that the power would be higher at low speeds. So it would be more like 700 kilowatts. And then as the car goes faster, the power drops at a rate of 48 kilowatts for every step of 50 kilometers an hour. You can see that. In fact, you see the curve here. And by doing that, and you can see, by doing that, I've effectively gone 1 second faster, which is so cool because it's free. We are not stressing the battery more, and it's 1 second faster. And it's quite difficult to see here, but the green trace is that faster lap time, which is a bit counterintuitive when you look at this because it goes slower in a straight line. But what happens is there is lap time gained exit of every corner because we've got more power at slow speeds. So you would find that the car accelerates faster, is in front of so the green car would be in front of the orange car exiting the corner, and then the green car would slow down in a straight line, but it would still remain in front. I think there's a question from Lauren. Yeah. Did you raise your hand, Lauren?
Oh, no, sorry. I think it's still from my first question. I'm not
Okay,
sure
no
how to
problem.
turn it off.
No, that's fine. Actually, no, sorry. It was a question in the chat. So I've got a question that says, does the lap time simulation use transient or quasi-static time independent model? So the answer to this is quasi-static time model. It's not transient. So the difference between quasi-static and transient, the quasi-static will look at there won't be any dynamic applied, for example, in the transition between acceleration and braking, the car will go instantly from accelerating to braking when it needs to. There will not be any there is no chassis movement. It's just a 1 point going around the lap. So we call it quasi-static. The dynamic is respected in terms of acceleration between each point and braking, but the transitions are not. But this is a method that was developed by Milliken 30 or 40 years ago now, and it's still used by Formula One teams. And again, for 424, look at how much learning we can do with such a tool. Now, all the optimization that I've talked about today, I've talked about aerodynamic optimization for the power we have, then we had the lift and coast, and then we had the power ramp. Every time I did this optimization, I then asked Damien or Augusto to drive in Unity, and we basically compared the result in Unity, and we found that the lap time gain or loss was the same or very, very similar to what I find here. But what we learn in Unity, we learn more. We learn, obviously, when you change the drag level of the car, there are other things happening. It makes the car maybe not as easy to drive. In fact, it will also change the tire degradation. If you have less drag or downforce on the car, typically you're going to slide more. It might be a car that is a bit more difficult to drive. And we know that you hear in Formula One when they go to Monza, the driver says, you know, how tricky it is because the car slides more and is more loose. When you had drag and downforce on the car, it's the opposite, and you've got more stability and less tire degradation as well. And we can feel that in Unity. We can also check the balance in every corner and things like that. But when it comes to optimizing for lap time, this is very, very good tool. And I hope you can see today why. I wanted to show you as a last point, I want to have a little exercise with you today and say, okay, but is there any other way we could cool the battery that could be, you know, more efficient in terms of lap time? And one way I haven't showed you here today is, and I'm going to put it as car number 6, is we could have changed the top speed of the car. You know, we can apply a speed limiter. So let's try and do it. So we're going to take car number 3, which is our reference before we had lift and coast and before we add power ramp. So I take car number 3, I copy car number 3, and I'm using it at car number 6. And what I'm going to do here is I'm going to reduce the speed limiter. We're going to have to do it by steps because we need to achieve the same power RMS. So let's say I'm putting 340. So I'll reduce the speed limiter. We're going to try that and see how it goes. So I'm running the simulation now. Got a shortcut on my keyboard for that. And now we should have a lap time here. Here you go. Lap time is 5 minutes 10, but the power RMS is still too high, 495. So I need to reduce top speed further. So let's go to 320. So it's just going to do it by steps, and in order to achieve the power RMS that we need. So 320, 466, very, very close. I want 465. It's very close. I could go one more step. I could do 319, you know, just 1 kph. Let's try that. So I was 466.8. I'm just dropping 1 kph, 465.2. Really happy with that. But look at the lap time, 514.8. this is 2 seconds, 2.8 seconds slower than this solution here. So you can see that, the features that we have created with the lift and coast is better than doing the speed limiter. What it looks like here is you can see that speed limiter comes here. Okay, so it's quite an aggressive speed limiter to reduce the battery temperature, but it's 2.8 seconds too slow. So we are not going to do that. Okay. So as I said before, so this is the end of this presentation on the offline lap time simulation. I hope you understand, the details of trying to gain the last half a second, and again, depending on the limitations we have with the electric powertrain and what we can do and build, and the level of analysis and details that is going into it. And it's not the end. As the project goes live, we're going to keep optimizing up to the last minute when we have to build a car, and at that point the car is frozen, and then we go. So I will not open the dynamic lab simulation today, but I just want to say that from the offline simulation, as I said, we validate everything in Unity. We get our drivers. This is really exciting for me because it's working like a works team with our test drivers and validating our models, changing the setups on the car based on the offline simulation. And again, as I said, honestly, 90%, 95% of the time we get the exact same answer, but we learn more. We get more comments from the drivers when they use the dynamic simulation. Okay. Remember that this dynamic simulation is accessible on GitHub. Anybody can download it and drive the car or use the autopilot. And again, the offline simulation is accessible for everyone, and you can make copies and start playing. I will show you, just to finish, how you can look at the scripts. So effectively, it's using it's the Google Sheet and the Google Apps script. So if you go here, you will effectively see the script that I have developed to compute this. So it's very short. I like to keep things simple and short, and effectively the code is fairly straightforward. Okay, I'm not going to go through it today, but you can see it's not too bad. It's not too long. Okay. All right. So I welcome any question on this before we wrap it up. Okay, so I've got 2 questions online, and then I'll come to the audience. So can we have some kind of tunnel so that air passes through the battery to cool it? Okay. So thanks for the question. Obviously, battery temperature, I said, is a limitation. There is already a cooling system to cool the battery. It will be a water cooled, or there will be a coolant, a fluid running through the battery, and then we have a big radiator on the sides, on the right-hand side, just to cool the battery with a fairly high-speed pump. So there is already a cooling system that's much better than running air through the battery itself. So it's a traditional radiator, air cooled, and then a circuit of fluid going to the battery cells. In fact, the Volkswagen IDR had an air cooled battery, and they were limited by temperature. They had to derate, and that one of the reasons is because they were just doing air cooling. They were not doing water cooling. Another question: could it be possible to use brake coasts on the bumps to optimize the cooling? Use the opportunity of speed constraint to reduce the demand on the battery. So I think what you're saying is, let's cool the battery when the car needs to slow down because of the bumps. In a way, we already are doing this, because when you look at the Unity speed profile, we are already reducing speed, as because of the bumps in 3 locations. But we don't want to reduce lower than this, because, well, we could look at But I already think that the answer would tell you that if you lower the speed even more for the bumps and reduce the lift and coast, your lap time will suffer because you're going to start reducing the speed, at already fairly low speed level, which is 300 kph here. And typically, you want to reduce speed at the very high speed points, which is why lift and coast work so well. You're reducing speeds when it's and at the end of the straight. For example, here you wouldn't want to reduce that speed limiter further because there is a straight after that, and we know that every lap time you lose at the beginning of the straight, or speeds you lose, translates in more speed loss further down in a straight line, which is why exit of corners you're trying to boost as much as you can, and you only reduce speeds just before the braking points. So I hope that answers your question. And then we have Wojciech, hi, raising your hands.
Hi, my question is related actually to the first one uh, about cooling the battery with air, but in this model you have tightly connected the drag level and downforce, right?
Yes,
Increasing down drag level always increases downforce,
this curve, yeah.
but you can add another dimension here, so you increase drag, keep the downforce in the same level, but increase the radiators for cooling the battery.
Yeah,
Thanks to this increased drag.
yeah, I understand. So let me open our CFD simulation here. Well, basically, the short answer is we're already maximizing cooling. So it would be very hard to get much more cooling on the car. If you look at, by the way, shout out to Alex, who's funded the restart of CFD here, following the aerodynamics module from a few weeks ago. There is somebody who will also add some credits to the CFD, and this is how the team is pushing together, and I love that. So we have restarted CFD and done more analysis in this past week, and you can follow that on pairing.com as well. If you look at typically, the car from the sides. So as you can see, we've got a fairly, I would say, from my experience, first of all, the radiator, as you see, is big. We have, when we talk about surface area for radiators, this is one of the biggest surface area I've installed in a car, and there's a lot of air going through as well. So we are measuring the mass flow here, and in fact, the numbers are coming out. Basically, this one, 2.18 kilograms per second of air. And again, this is a high number. So the other thing you need to know is the cooling of the battery, the main limitation is coming from the inside of the battery. We actually have a very good amount of air cooling. What we can do is getting radiators that are a bit thicker, maybe a bit heavier, so we'll look into this. But once we've gone through the radiators, there's a lot of heat transfer there with the air. But when we go into the fluid system, the main limitation, the main resistance in the system when you talk about cooling happens between the coolant and the battery cell. So it's not aerodynamics, it's purely battery construction and battery design. Okay, so I hope that answers your question.
Yes, so it is already at the limit.
It's already at the limit, yeah.
Thanks.
Okay, anybody else has any question on the lap time simulation before we wrap it up? But I hope you understand yeah, again, the details into optimizing, and I'm really excited about showing you this, because if we don't do this sort of analysis, we lose, we don't fully gather the opportunity of performance. We might design a car that's 5 or 10 seconds slower very quickly because we haven't optimized all these parameters together. Okay. And I really personally, I love the strategy of lift and coast and power ramp, and this is all the software we've built as a result for Unity is exactly the software that will go in 424, the real car. So the power management being developed in Unity is already a lot of time gained for us, because we're going to put that software into the 424 car. Obviously, we'll adjust parameters in real life, but that work is extremely valuable. Yes, Martin?
Hi, Nico. How it's going?
Hi.
As you were explaining that power drop, are you going to use that? I guess it was like 50 kilometers, or are you going to optimize that? I mean, to do the step shorter.
So the power, so you're talking about the power ramp here.
Yes.
That slope here.
Yes.
So how quickly the power drops. Yeah, effectively, I have actually done a few steps. We could do one here quick, actually, just for fun. So typically what I do is I'm very much a manual optimization guy, as you can see. I know we're at the age of AI, and we always have these discussions, and people say, AI could optimize things so much quicker for you. But believe me, it's a craft at the end. You just want to, it's not about getting AI to learn it for you. You just want to understand the sensitivities in both directions, and then you make, I think, better decisions. Even though AI, I'm sure, will help in the future, but we are not missing out a lot by not using AI doing this for us. I hope you understand that. But let's have a quick play here. So there is this 48 kilowatts per 50 kilometers an hour. Let's say we say, let's be a bit more aggressive to start. So instead of 48, I go 53. And I do that. So now I've got 445 kilowatts at the end of the straight. So the car will go slower in the straight. But obviously what it will do straight away is the RMS is going to drop. So I know I will need to change my lift and coast back up. So say 275, and then we'll adjust it. Let's run this. And to be honest, I'm not sure. We might find a bit more lap time today, but I think I've done this before. Okay, so RMS is still a bit high. Okay, so I will basically need to lift and coast a bit more. So I'll go to 270. And RMS is now slightly low, but we're 0.2 of a second slower compared to our baseline. But you can argue that we've got a RMS a bit low, so I guess you can now start playing with a finer step on the lift and coast. Let's try that. Sometimes the lift and coast can be a bit coarse in steps, so we'll see if it sort of jumps above. Actually, the RMS hasn't changed, so I go 1 more kph here. I rerun all the themes each time, but you can see it's very quick. Okay, I'm really close now, 464.9, 1/10 of a second. It looks like it's pretty much neck and neck. So it's fairly flat. I call it fairly flat. So I've changed the slope a bit, and the lap time is more or less the same. So you can see that maybe we're on a flat part of the optimization. Maybe we're at the bottom of the optimization curve here. So I hope that answers your question. But we can keep going with this stuff, and find a 1/10 or 2 of a second, I'm sure.
Okay, Nico, thanks.
No worries. Okay, I've got a question here on the chat. So, how is the software? So, how the software will recognize on track where it should release the power before the driver brakes, like in your simulation? Okay, great question. Thank you. So, what I've done is I took this simulation here, and I looked at the distance. So you see the distance going from 0 to 21 kilometers. And you can see at that point, we are at 3,000, we are at 3.3 kilometers exact. So there's one point here, there's another point there, another point there. So it's the distance at which we lift and coast. But obviously between this simulation and Unity, the speeds are a bit different because the corner speed is a bit different. So we'll have to adjust further. But what I did is I took these points and I went to Unity. So I'm going to share Unity now. Let me share Unity. Here we go. I also need to go in the correct branch on GitHub. I'm already in the correct branch. Okay. And what we have here is in Dynamics, we've got a list here of speed limiter segments. So what the car knows what is the distance, the lap distance. So just when it crosses the line, it goes to 0, and then it accumulates distance based on car speed. Which is why, by the way, for those who are following the chat on the AI speed estimator, it's very much for that. We need to find a way to estimate the speed of the car based on wheel speeds so that we can integrate it and get the distance. Once we know the distance, the car will automatically apply a speed limiter or ramp of power down. So each time there is a segment, it goes between a certain distance, so 750 meters to 1.5, which that's basically the first lift and coast point. And the 0.7 is the speed, the target speed, or the speed at which power will come back on. It's 70% of the top speed. So it's effectively 70 meters per second. You know, the top speed is 100 meters per second. So we've got one segment here. This second segment is the one for the bump. And then we've got another lift and coast. All the 0.7 are lift and coast. So what I've done is I've adjusted the distance to start, which is when the power goes to 0. And then the distance to end is the mid-corner, the middle point of the corner, because I want to make sure for the next straight line, there is the power is full again. So I've done that. I had Damien driving, and I had to readjust the distances to get the braking speed I wanted. If I show you what it looks like on telemetry, I'm gonna run the telemetry a bit. Let's go on this view, and let's go with autopilot here. So we're going to look at so this is I'm going to stop here for a minute. On the battery page, we now have a power RMS channel. Again, because we will want to look at this for optimizing the temperatures. What you will see is the power battery is going to drop to 0 in a straight line. Okay, so the car drives, and we're going to arrive at a lift and coast point very soon. Just about there. Okay, I'm going to stop here. So you can see the battery power went from, by the way, you see the ramp. You see how the power goes from 693 down to 530, and then boom, it goes to 0, even though the driver is still at full throttle. The driver stays at full throttle to keep the DRS open. if it releases the throttle as well, the DRS will close. So it's not the driver releasing the throttle for the, it's automatic based on the torque maps and the power, the speed limiter. So all of this phase here is a lift and coast. You can see the speeds reducing a bit, and then there is a breaking point. And if you look at the speed of the car, you don't have it here because it's this is not a speed trace. Let's go here, 260 kph. Okay, so it's not exactly 265 in this case. I've adjusted the points as well for power RMS. And then I kept going. So let's keep going. You will find that I will accelerate here up to the next lift and coast. And it's coming. Here you go. Now we're coasting. See the speed going down and then braking. If I stop here, the braking speed was 254. So what we'll do at Nürburgring in real life is we're gonna have to adjust manually. There will be an engineer just dedicated to that. After the first lap, we're gonna adjust the points for lift and coast. And obviously, as the driver goes faster and drives better, this will move a bit because the speed in a straight line will change. So it's a manual work. As long as we know what we're targeting, which is the braking speed, then we can keep adjusting. And as a final thing I want to show you is on the battery page, you see I'm gonna make it a bit clearer here, if I can. If I zoom out a bit, you see this trace is power RMS. And you can see that power RMS is 476. And then when I lift and coast, it drops down to 445. That's how we cool the battery. We just keep the RMS low. And obviously, as the car continues, the power RMS is stabilizing to a number. Okay? Stop it here. That's how we do it.
Isn't it a bit risky to rely on distance calculated with integrating speed, and a slipping of the wheels here and there can change it by a few hundred meters?
Yeah, so this is why we are going to have this speed estimate. So the speed estimate function we're creating is correcting for wheel slip.
Mm-hmm.
And we've already done some tests. So what we've done is we've run a few laps, different, locking. By the way, these cars tend to run the laps in a very similar way, lap after lap. But yes, you're right. Sometimes you brake a bit harder, you're going to lock. There is a bit of slip going. And we've trained a little AI model with a few laps to estimate speeds based on these different channels. And we're also using accelerometers in that. And what we find is the error on lap distance over the full lap, so it's 21 kilometers, is about maximum 50 meters over the full lap. So all these braking points will be, within 5 meters maximum of error. I would imagine. So it's really good. And by the way, this will only change slightly the battery temperature, but it will not affect the driving because the driver will still decide when he wants to brake.
Mm-hmm. Would it be safer still for the driver to have dedicated button on the wheel for the coast mode?
So yes and no. At Le Mans, typically yes, because there's only 3 or 4 straights, so it's very easy for the driver. At the Nürburgring, this is why we have auto DRS as well. I want the car to manage these things automatically because I want the driver to just have to think about his driving.
Mm-hmm.
And it will do a lap, and then we'll look at the numbers, we'll adjust, and then he will redo a lap, and things will move a bit around him, but not much. And it's, by the way, this is what Formula One does. They have segments. I've done it, 10, 15 years ago, and they're still doing it these days. They have segments. When you hear the driver saying, I want brake balance +1 in this corner, I want my diff to close in this corner, they do it based on distance. It's exactly the same principle as what we're doing.
I didn't know that.
Yeah, and Le Mans cars do the same. The car changes setup based on lap distance. And there is a table of segments. It's exactly the same principle. They even use a small AI model as well to predict speed. Because they cannot measure, you cannot measure true speed of the car. Well, the best you can do is look at, with a speed over ground sensor, look at the speed of the track with a visual optical sensor. But it's not allowed to be used. It's not allowed in F1 during the race. It's allowed during testing. So no team is using this during the race. So everything is done on estimation of speed based on wheel speeds and accelerometers and things like torque and brake pedal, throttle. You can use this as well. Okay.
Mm-hmm.
If you have any last question before we stop.
Just about testing, doing multiple laps. How do you plan to, as the battery capacity is only for the one lap and some margin? How do you plan to? Is it replaceable or something like this?
No, the battery is not replaceable. The battery is more or less like an iPhone. You have to go back to the factory to change it. It's extremely integrated. So when we go to the Nürburgring, we'll have done a lot of testing before. When we go to the Nürburgring, we'll be 95% there for lap 1. We'll have already set up all our numbers. The driver will go do 1 lap, and then we'll have an hour and 20 minutes before we do another lap. And we'll do maybe 5 or 6 laps in one day. So we'll have to have a lot of preparation before. This is why driving simulation is very important. A lot of, first tuning will be done in simulation, but then we'll also have a lot of straight line. So we'll start with straight line testing in the UK. You can do a lot there to check downforce, drag, powertrain, software, etc. And then we'll have track testing in the UK. Then we'll go to Spa-Francorchamps and do a day or two there, and then we'll go to Nürburgring. But we are not going to wait to be at the Nürburgring to tune the numbers I've talked about. We'll already have a very good model of the temperature we expect at the Nürburgring, the battery temperature, based on the testing we'll have done before. So every 5 minutes or 10 minutes of testing we'll do, we will learn and recalibrate all our models to then do much more in simulation and get the car ready for the Nürburgring. Okay.
Thank you.
All right. So listen, thanks everyone for coming here today, and I'll see you in the next one. All right.
Thank you.
Thank you, Nico.
Thank you.
Thank you, Nico.
Thank you so much, Nico.
Bye.
Bye. Bye-bye.